So if I have a method call like that, and now I want to translate that into a sequence diagram. Then, and this here is foo. And this is something colon some type. This is something colon some type. Where does the A go? Okay, does it go in this box or in that box? All right. So this is the kind of question that you simply need to know to be able to get any points on question number 2 on the exam, right? Would everyone agree with that? That if you can't answer that question instantly, you can probably kiss your chance of getting points in question 2 goodbye. The correct answer is it goes here. If you knew that and still managed to mess up the exam, then that's a problem. If you didn't know that and you didn't get many points in question 2, then you got what you deserved. Right? You simply have to know them instinctively, without thinking, at this point. We've had numerous exercises with these sequence diagrams. And so if your exam prep is so that this is not fully automatic, there's either a problem with the exam or with your exam prep. And I put it to you, it's with the exam prep. And so now where does this come from? And so first of all, just to see where should you have known this from, it's in the book. Let me get the thing from the book. And I can't find it now. So I actually put this out. Oh, so I thought. No, it's the wrong chapter. Shima 2. So here we have a sample sequence diagram, right? Where we're having the mailbox, and there's some call to add somewhere, and here we have the new message. That's a message queue. And then we see in the text a little bit further down, and it says new messages dot add. Notice the word new messages. Notice the word new messages, right? Now here's the thing. That and this is just kind of a normal, junior level textbook, and it's written the way that any number of junior level textbooks are written, in that it assumes a fair amount of engagement by the reader. So the assumption is that when you read such a book, that particularly now that it's online, right? In the olden days, the book was printed on paper, and you could just maybe when you see one of these things, you could kind of make a make a note next to it, so that next time you remember this, right? And you might have made a note that says new messages dot add. And now you might ask yourself a whole bunch of questions, right? Like, what's the significance of this object here? Why are we having two objects? There's only in the method call is new messages dot add. What's this thing there for at all?
That's the container that satisfies the pattern.
No, because this thing may or may not have anything to do with the design pattern. This is just a general notation for any method call. The sequence diagrams are just notations for method calls. Patterns are not. So what is the significance? Why we? What does this here have to do with a mailbox? All right, so this would be a really good question to ask yourself when you read through this material. So that is what's expected when someone reads through some material, that when these questions come up, A, that they come up in the first place, and B, that you ask them. So I'm making a big deal out of this because this is a very typical thing that happens at this transition where you all took lower division classes where there is a lot of spoon feeding and there's a lot of there's not as much independent reading as there is in the upper division classes. But now you are expected to make that transition to become more engaged readers and to develop the skills to take this kind of material apart and to question what you read. So the way I like to say that is there's a big difference between glancing and reading. So reading means that when you look at this, you ask yourself and says, what is the significance of this thing? Why the heck didn't he put a type in here? Why is there a colon and all of that stuff? And ask yourself those questions and then answer them out of the context. If you don't read at that level, you're not reading. And you really have to do that. Now you might say, why do you have to do that other than that Horstman tells you that? And so I'm glad you asked. So recently I had to learn how to do something with Amazon Web Services. And what does Amazon give us? It gives us pages and pages of stuff that looks like this. Right? It looks suspiciously like a textbook. Why does it do that? Why doesn't Amazon give us what we would all love, namely a bunch of YouTube videos?
YouTube videos take too long to reference.
That is the problem, right? So you think of your video player here, and then you think of the text with navigation and all of that. So the problem is, it takes long.
On the soap of the transition player, you kind of have different programming languages that can be used to implement the Amazon APIs.
Very good, right? So it's difficult to do it with multiple programming languages. What the Amazon people do is then they'll have little tabs where it says Java or PHP. And so it's difficult to navigate these things, right? So these are hard to structure. Right? There's only one linear structure. If you wanted to branch off in any old way, that would be very difficult to do in a video. Another reason Amazon doesn't do a lot of video is they're hard to update. What if there's a change somewhere? How are they going to go through every video and update whatever that minor change is? So there. And so they don't usually do that. And that means if you want to learn something that's new, something that's fairly complex, you have to learn how to navigate text. And it's different. It's just something that everyone has to get better at. And in the olden days, when there were no videos, students who came into college, had, because they had no other choice, they had to have mastered that in high school. These days, probably in your lower division courses, there are a lot of videos. There are a lot of quizzes that you can take that give you instant feedback of whether you were right or wrong. And that's great when that's available. Amazon does not give you a lot of quizzes that tell you whether you're right or wrong. Right? That's expensive to produce. It has to be updated, and it's just not worth it at a higher level of technical expertise. They give you textual information, something that you need to navigate. So we all, one of the goals that has nothing to do with the course, but just with generally being a learner that you have in college, is to learn how to get better at these things. So whether you like it or not, you're going to have to do a better job navigating the book. And yes, I could record it all in a long, 2,000-hour video or something, but that would not be super useful. That actually, every once in a while, one of my publishers says, "Can't you make a video series of something?" And I'm always amazed when I do that. So how little I can cover in a video. So I have a video series of 40 hours worth of Java. and it covers maybe 1/10 of the book. And it doesn't. I mean, and basically, it's all I can say is, this is difficult. Here are pitfalls. Have a closer look at that. And when you watch it, I don't know how much you get out of it, but people still do like to watch it, and I'm not totally sure how effective it is. But that's, let's hope someone gets something out of it. But there is a limit as to what you can get out of videos. Videos are very good for high-level things, like the kind of thing that I'm doing right now, where I speak with emotion and I want to shape up. They're not so great for detailed technical information. What's really pretty good for detailed technical information are these kinds of things. Books, white papers, where there's a lot of information density, there's navigation, but it's not automatic. And you really have to force yourself when you read something like that to figure out what is the important stuff, what don't you understand. And so you have to sit there with, since it's hard to mark on the screen, I usually just have like one of these notebooks, as it happens I have one with me, and as always, just make some notes. What don't I understand, and I doodle and that kind of stuff. You need to figure out what works for you. There's no workaround for that. It is an important skill. So, with those sequence diagrams, so I really, there will be another chance for you to fail on the sequence diagrams, so I want you to figure those out. It's an essential skill to be able to draw these things, and it's not rocket science. You have a question? No? Yeah? Oh, sorry. I thought one of you. So reread that section and figure out what is it that you didn't do right the first time. What was it that blocked you from getting the perfect insight on how to do this diagramming? Because, of course, with this diagramming, I could teach you. I could give you worksheets and mark them as true, false, and you could learn them the old-fashioned way. And then you would know how to draw sequence diagrams with precision. But that's not really my interest. My interest is that you can teach yourself how to draw them. And so if you have questions, by all means, put them on Piazza, and I'll be glad to talk about it. But this is one of the things where I want you to learn how to learn things. And so there's a meta thing that really, when you think about what are you going to have, what do you remember from college in 20 years? Or the other question, why does someone at Google want to actually hire someone who's gone through college? When in fact they could probably perfectly well just get someone who knows how to use JavaScript and CSS and whatever it is that they need that person to do. Is they want to have someone who can't just do a specific set of things, but who can teach themselves new things. That is the more important thing that you learn at college. So it's more important for you to learn than it is to have any specific set of knowledge. And so if you're ever at a Google interview and there's some fiddly thing that you happen not to know, then they will probably not press you on that. They'll say that's fine. No one can know absolutely everything. I mean, if it's something super basic, then that would be weird. But I mean, if it's something that's specialized, they would perfectly well understand that. But what they really want to find out in those interviews is, can you think about how you're thinking? And that really is an important skill. So I want you to go through that, and since just about everyone did a terrible job with those sequence diagrams, is go back to the basics, reread that chapter, that section on sequence diagrams, and figure it out on your own. And I'll be glad to talk about it more in class. But I want you to take the lead on this. All right. So that's the thing with the sequence diagrams. The other thing that perturbed me, and I'm not totally sure, whether my theory of why this was troublesome is right or not. So that was the thing with the representations. Oh, before doing that, so my expectation was that to draw a sequence diagram takes 5 to 10 minutes, and I think that's a totally unreasonable expectation. You should be able to draw any sequence diagram that has less than 10 arrows in 5 to 10 minutes. And so if you can't, then you need to draw more sequence diagrams. Did I suggest as exam practice to draw a sequence diagram?
Yeah.
Did that help?
Kind of.
Obviously not, right? So what did I do wrong? My guess, though, is that if anyone has done those and drawn those, they must have been just as wrong as the ones that I got in the exam.
Yeah, I think that's a problem. Like, you ask us to draw sequence diagrams, but then we draw them and then...
All right, so here's my expectation. Number one, that when you draw, I fully expected that people would get confused drawing these sequence diagrams. because they are confusing. If you don't do it right, you kind of feel that it feels weird, and it just and at that point, just put it on Piazza. There's no shame in putting a bad diagram on Piazza. You're going to get, there's 27 people in the class. If you ask a really dumb question on Piazza, 26 people will thank you. I swear. 27, because I will also thank you. What's not to like? It's anonymous. No one will know your name except me. And I don't care. And I honestly don't. If anything, I say, oh, this is the person who asked a good question. You know, what's wrong with that? So you really need to do that. You need to, a few days before the exam, you need to start working on some of this stuff. And when you're confused, just put something on there and say, this is confusing. Because it doesn't get any less confusing during the midterm. Right? It's not that out of a sudden, like the fog will lift when you see the magic words midterm, right? That's not how the world is built. So by all means, do that. It's not kindergarten. We're not asking trivial questions. It's not multiple choice. So you really have to be able to do things. Yes?
Considering that it's hard for everyone to find the sequence diagram, is there a good resource we can find for people actually doing the correct sequence diagram?
Yes.
There's going to be lots of people doing that.
Yes. Okay. So the question is there a good resource to draw correct sequence diagrams? And that resource is your textbook. What I really want you to do is I want you to read the textbook. And I want you to do that so that you learn how to decipher something where it is explained fully but maybe not spoon-fed. That is a skill that I honestly think you want to develop. And this textbook has been reviewed by dozens of professors. They all thought it's great. And so it's not that the textbook withholds essential information. It is just not a step-by-step cookie-cutter guide. It assumes that the reader makes their own inferences. And so that's every technical documentation that you're going to be reading from now on is going to do the same thing. And so that's really what I want you to do. If that fails, I would be glad to have a session on step-by-step sequence diagrams, but that's really not my most important thing. Yes, you need to understand that notation, but what I really want everyone to work on is to get better at decoding this kind of compact, dense technical information that you're going to find everywhere. So let's give that a try first. And if it fails, then I will give, I can write a cartoon guide on how to do sequence diagrams so that anyone can do it, but it shouldn't have to come to that because it doesn't scale. So that's my concern. So work with me here. Let's give this a try. And then, maybe the next edition of the textbook, I will make this particular subject less opaque. So the other thing that I don't know what that I found problematic was this thing with this array implementation, right? So we have in the olden thing we had an array set, and so we just tossed in these elements as they came along. And that was the old set implementation. And the one that's in the exam, what was the difference?
You sort them when they're going.
It was sorted, right? So at any time, it was sorted. And now, how do we know how to insert a new element?
Binary search.
Binary search, right? Binary search finds the insertion location. It either tells you the element is already present, or it tells you where to put it. And as it happens, and the way that the Java standard library does it, it does that thing with a negative number. I didn't think everyone necessarily was familiar with that part, so I spelled that out because you might have had your CS2 and C++, and I don't have any recollection how this works in C++. I could look it up, but so any binary search has this issue that it needs to be able to tell either whether the search was successful or if it failed, where the insertion location would have been. Because otherwise, just saying it's not in there is not good enough. You want to know where to put it. And so a lot of people kind of got that idea, but what then surprised me is I then started grading this, and so I looked at test, which was the first one. And I said more than half the people in the class for test left the linear search in place. And I didn't get it. Why? So here we have one of the problems that I said was going to be on the exam is re-implementing the internals of a data structure. Same set of public methods, different internal implementation. And so then when you look at the methods, then you need to see what's the impact of the change of implementation. We had did we have a homework? Yeah, of course, the bit set and array set, right? Same interface, different implementation. Same thing here, right? Same interface, different implementation. So when you see test, and I'm assuming that everyone knows binary search. Was there anyone who didn't? Maybe it's an unfair question, but I have to say, if you didn't know binary search, then I realized it must have been a nearly impossible problem. And so I do kind of have to assume that you know, like, your basics from CS2. So if there was, I would be interested in if someone wants to anonymously tell me that binary search was a problem, if I can't rely on something like that. So I generally, assume that was obvious, but if not, I'd like to know so that I know next time. Just post something anonymous on Piazza or something. So once you know that's binary search, then now for test, that's one line of code. I've given it to you in the solution. For set and clear, it's a little nastier. What's the problem with set and clear?
You have to shift all the elements.
You have to shift these elements. And what is the great unpleasantness in shifting these elements?
Takes linear time.
No.
You have to use the array copy.
Well, the great unpleasantness, you have to know how many to shift. Well, it's not the length. It's the length minus the insertion location plus minus 1 or 2. Right? And so if someone during the exam makes the calculated decision and say, I always get these index values off by 1, that would be me. And you just skip it. That's fine. But then do all the rest. I mean, how hard could that have been? You just would call binary search. You now put it all in. You remove the minimum and maximum calculation because it's now, of course, the minimum is always on the left and the maximum is always on the right. And then you're done. And so you would have lost 4 points. But almost no one got this one within 4 points of the 4 points. There were a lot of people who had problems with this. And it's not totally clear to me why. Because you studied the thing. I think everyone knew what the array set implementation was. I hope, right? You did it. I did it. I didn't think it was difficult. But then the binary search thing threw a lot of people off. Yes?
Honestly, for me, what made this problem hard was that I finished 1 and 2 and I had 20 minutes left and I panicked. Honestly, I didn't even read all the way through number 3. It said binary search, and I started implementing binary search. And then once I realized I didn't have to do that, I had 10 minutes left.
I see.
And then I wanted to do number 4, so it's like...
Yeah. That does happen in these exams. Because, it's 5 problems. It's not like 30 multiple choice problems. And so my strong advice is that, number 1, you first read the entire exam. And that you brutally budget yourself. If you're not done with something after 5 minutes or 10 minutes, figure out whether you're not better off moving on. Because if you're trapped yourself in a situation where you spend most of the time on 2 problems, and then you also did those 2 problems wrong, then that's really bad. So, again, I think the first 2 problems should not have taken anyone longer than 20 minutes. A couple of you were smart enough to say, well, I can't do this with a tool, so I did it on pencil and paper. That clearly is an option, although how long can it take you to do it? I don't know. That one, I think, was utterly practicable. And I'll do it, there'll be another midterm in a few weeks, and I'll do it the same thing, that the first couple ones, you could practice them so that you could just do them on autopilot. The programming one is always a bit of a crapshoot because you have to read through a bunch of code, you have to do it. Then the next advice I always have with programming is get it written down first and don't waste a lot of time. Sometimes I find people, they have like one bug and then they spend 20 minutes messing with the one plus 1 or minus 1. And that's, of course, not effective. Yes?
For your study for number 3 was the binary search method, like was a little off on like what exactly you returned and how it kind of worked.
Oh, I see. So I thought that I was very clear in just giving you the piece of code that you could just paste in. Did it? Okay. So
I read it over and I looked at other documentation and it made no sense. And then, I don't know. I feel like if I would have been able to look it up online, then it would have made some.
I see. So you looked at? Did you have the Java doc locally? Is that what you looked it up?
Yeah, I did. It was just like.
Yeah, that one is it's probably harder to read.
Yeah.
Yeah.
I just like removed the method after. It just made it more clear.
Okay.
Made it more confident. Made it much easier to understand.
Okay. And it is that thing with the positive and the negative.
Yeah.
Yeah. That's why I thought, and I give you the code and exactly how to compute. Okay. Well.
Which is like, I'm like,
Yeah. I do realize it's a danger in any exam that sometimes in the heat of the battle you look at the question and then you're not totally clear about it. Yeah. The other thing, though, is that to do well in these is really to carefully look at the solutions that you get. So the advice that I gave you is take your solution, compare it exactly against mine, and see how you did it different. Did anyone do that? Is that effective?
I did that in a couple a lot.
Uh-huh.
I got awesome points where I couldn't easily got them.
Yeah. Well, we'll have another one of these, and hopefully then that'll go a little better. But the one thing that I really want to try harder is to get this textbook learning to the next level. So I would try to make that a little bit more explicit as to what you need to do. We'll see how that goes. At this conference where I was, there was some discussion about that, where some professor said, well, today's students don't know how to read anymore. And to some degree, it's probably true, and I'm the first offender there, because when the CS1 textbook that I'm publishing, and we're trying to make everything more interactive and less text and all of that, because learning to program is very, very hard. So CS1 is the hardest course probably that most students take. It's much harder than this course. To go from no programming to being a competent programmer in 15 weeks is super hard. And so that one needs all the help that one can get. This course in comparison is easy, and so we can smuggle in some of these learning to learn things. All right. That's really true. It's also the hardest course to teach. So in hindsight, thank you, CS1 instructor. No one's worked as hard as he or she did. All right, now on to the next sections. To motivate this, has anyone looked at the homework?
6.
Yeah. Okay, so at this point, everyone should, of course, have started out a directory HW6, put in a few of the files, and checked them in. Right. So if you haven't done that, make sure to do that this afternoon. If nothing else, it makes you read through the assignment, and that back part of your brain that is otherwise underutilized when you take a shower or whatever can slowly start thinking about how to approach this. This is not a super hard homework assignment. It actually is probably less than 50 lines of code that you need to write total. But as always, it matters which 50 lines of code. And it follows closely what goes on in the book. So this will be like a really good opportunity to try out this, let's read the book a little bit more carefully strategy. Yeah. So since I said in the conference, so there was one person who said, the students always want me to give them videos. And so, like we talked about, that's probably not the most effective way of doing it. And so, but that person dutifully recorded a bunch of videos. And someone else said, the students always want me to give, and that really struck me as weird, want me to give them the PowerPoint slides. That I didn't get. What earthly good can you get out of a bunch of PowerPoints? The PowerPoints are just here as a backdrop for me so that there's something behind me when I talk. But that's their only use. I mean, otherwise, the book has all the information. The PowerPoints are just have a bunch of words. And so I used to have to, when I was working in industry, I had to get out with the CEO and the salespeople, and I would sometimes make my slides. And every time I would make the slides, the CEO would count the number of words of them. And when there were more than 40, he would rip up the slides. I had to print them out. And so there's nothing on the PowerPoints, right? It's not a source of useful information. And so if you try to study from the PowerPoints, that's a futile thing. Then you just get the kind of stuff that you didn't need to read. That's the obvious thing. All right. Strategy pattern. So we have to observe a pattern. So I'm going to first come up with a motivational example for the strategy pattern. Then I'm going to tell you what the pattern is, and then I'm going to tell you where it occurs in the homework. So here's the motivational idea that in Swing we have user interface components, that's buttons, sliders, text fields, and so on, and we need to arrange them in some way. Now, how do you arrange a bunch of components? I'll just show you like some user interface. So here you have a user interface, you have buttons, and you have more buttons, and you have text areas. In some versions in some user interface toolkits, what the designer of a user interface does is they have like a tool, then they can drag a button here, and then they drag the next one here, and then they drag the next one. And then they can like select all of these and say, I want to make them all the same size. And then they just all get put at a particular pixel position. And so that was fashionable 15 years ago, but it doesn't, there's a huge drawback with that, and that is that when you have a graphical tool that puts these here and remembers the pixel sizes and the pixel positions, then it only works well for one particular pixel layout. So if you have a high display screen, then the pixel positions don't do you a lot of good. If you translate the user interface to Finnish, where on average the strings are twice as long as they are in English, then the pixel positions don't do you a lot of good. Or if you translate it to Chinese, where on average they are half the size as in English, then it also doesn't look all that great. So there are other user interface builders where the tool tries to learn your intentions. It tries to remember that you said, make these all the same size, because that's the command that you issued. And then it puts a command into the dialog that says, make sure these are always the same size. But that's not all that common. That's hard to do. And so when Swing came out 20 years ago, they said, that's too hard. Instead, we're going to make it so that the programmer lays out the user interface, and the programmer has to say how this should work. And so the way the programmer does that is with a bunch of layout managers. So you have a container. The container has a bunch of components. You toss them all in, and you just say add, 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 add. They're all in there. And then one says that the way the layout should work, that there's different strategies for doing the layout, and there's a flow layout and so on, that a box layout that will do different things. So here's on this picture you can see the flow layout just puts them all in order. There's a box layout that puts them all vertically or horizontally. There's a border layout where you can nominate where they should go, and you have 5 places. There's a grid layout that puts them in a 2-dimensional grid, and then there's a grid back layout that works kind of like HTML tables, where you can specify row spans and column spans and row widths and that kind of stuff. So you have these various kinds of layout managers, and if you were like a professional Swing programmer, you would have to learn how to use them. We're not going to do that in this course. I just wanted to tell you that's the basic idea. And so the way you program that is you set a layout manager to the component, to the container, in this case the panel. Then you just add all of the components, and now the layout manager lays them out. This is a grid layout, so it'll space them out 1, 2, 3, 4, 5, 6 in a grid. So that's certainly a simple enough scheme. So we have a JPanel. That's a special case of a container. Every container has a layout manager. That's an interface with a bunch of methods for achieving the layout. And then the various layout managers themselves, they implement this interface. So in the book now it goes on and shows how to use that to build a GUI for this voicemail system in chapter 2. And here you see it in all of its beauty. The way this is achieved is by having a box layout of this thing, a panel which itself has a further layout, a box, and then this text area, and then here another panel that has further sub-layout. So by nesting the layouts, you can put things together of pretty much arbitrary complexity. The book then makes a point that by itself is an interesting point, where it says that, by the way, the phone system, all of the back-end code is completely unchanged. Only the thing that previously was the connection now needs to be rigged up so that it no longer talks to system.in and system.out, but instead communicates with this thing. That is an interesting thing, but it's not something that right now that we want to stress. I might come back to that later. So as you read through that section, you have permission to skip past it. that part, or just remember that's kind of a generally interesting thing. So we don't care about this voicemail system GUI. There's also then something in the book that talks about how you can make your own layout manager. And the only takeaway that I want you to have is that that is one of the motivations for what the swing people did. They said, we will come up with the most common layout schemes, but what if you have something different? And as a motivational example, I give this layout that seems kind of useful, where you have right justified labels and left justified text fields, and I show you how you could implement that layout manager. It seems plausible that it should be doable. A layout manager's job is to take a bunch of components and to move them to the correct place. So what this layout manager does, and you don't have to study it in detail, is it compute what is the maximum size of these, what is the maximum size of these, to figure out how to split the dialog, and then it moves them to the right places. You don't have to study that code in detail. The idea is just that anyone can achieve any layout that they want. In a different book, I have a show how to make a layout manager that arranges all of the components in a circle, which is, of course, completely useful, but it looks appealing. The beauty of the layout management scheme is that you can do it any way you want. Contrast that with layout managers that you find in other toolkits, for example, in Android. In Android, there is a number of schemes that are pre-canned, and they're not trivial to extend. Someone could extend them, but it's very hard. In the Windows GUI builder, there's no way you can extend anything. If you do layouts in JavaScript, you, of course, do them in HTML. And there, again, you have a fixed number of layouts, whatever it is that you can do with HTML and CSS. So the Java people had said, we have a setup that's completely flexible. You can take one of ours, or you can bring your own. So this interface here has a method called layout container. That's the important method that does the work of arranging all of the layouts. And then it has a few others that, for adding a component, removing a component, that seems pretty necessary. Maybe not. Maybe you could do that on a different level. Anyway, they came up with this API that we don't particularly care about. The reason I put in the layout thing here is it's something that every Swing programmer is familiar with, and more importantly, it motivates this design pattern. So, in this, if we abstract a little bit, the layout management, what is it? It's an algorithm. And different people prefer different ways of carrying out that algorithm. Sometimes you want the layout horizontally or vertically or in grid or in whatever. The different ways of achieving the same general goal. And it's the layout manager object that's responsible for executing a particular way of doing that, a particular strategy. And so there is a design pattern called the strategy pattern that wants to get at this idea. So the strategy pattern generally applies if there's more than one way of doing something useful, and if you want the user of the mechanism to have control over that they should be able to plug in whatever strategy they like. So another example of the strategy pattern is with comparators. When you call collections of sort, and you give it a comparator object, so that the sort can compare by country, because countries can do it by size or by area or whatever, that the strategy of comparison is pluggable. So out of that comes the general strategy pattern. And so this is, again, something when you read through this in the book, these are kind of dense to read. I find it a really good idea to go and take it out a sheet of paper and try to come up with, what is the correspondence in a specific example. It would be really difficult, I think, to understand this in general without working out an example in your hand as you read this. And really, that's why I say I take my notebook, I open it up, and I just start scribbling. There's, all sorts of scribbly stuff in here that's not very useful afterwards. Just so that I keep myself thinking that a class can benefit from different variants of an algorithm. Well, that is complete abstract general nonsense. Right? That could mean anything. And so the best way to understand that is to think of an example. So let's think of the layout management stuff. Which is the class that can benefit from different variants of an algorithm? Who is the client? Okay, so now everyone agrees this is a good question? All right, so this is a great question, right? So let's go back to the layout management. So we first learn about layout management, and so this is all general nonsense. Do we have some code somewhere? I always love it when we have code. All right. So here we have a key panel. Here we have a bunch of buttons. And here we have the grid layout class. Of these three classes, the panel, the button, and the grid layout class, let's now try to identify which is this class. Grid layout. Okay, so some people say the grid layout, some people say it's a JPanel. Now, who benefits? Does the grid layout benefit? Not really, right? Because what's the grid layout going to benefit? Say, hey, I get to lay out some stuff. I mean, that's what it's supposed to do, but that's not a benefit. The one who benefits, okay, does the button benefit? Maybe, right? The button gets benefits by being in the right spot, but it sounds more like it's the container that benefits because its components are being laid out. So in this case, that would be the JPanel. Clients sometimes want to replace standard algorithms with custom versions. Who the heck are clients?
Anyone trying to use JPanel?
Yeah, anyone, a programmer who wants to, do this kind of stuff, I guess, right? So this would be a programmer. And what are the standard algorithms in all contexts?
Flow layout.
Yeah, exactly, right? So flow, grid, and so on. Yeah. All right, so now we define an interface type that's an abstraction for the algorithm. What is that interface type? We have to go back. This one, your layout manager. Okay. Actual strategy classes realize this interface type. So what are the actual strategy classes?
Would that be our standard algorithm?
Yeah. Or the custom ones. This one or the ones that we had on this picture. All of those are actual strategies. Okay. Clients can supply strategy objects. So the client is this programmer, and the programmer who's dissatisfied with the standard choice can supply their own. Whenever the algorithm needs to be executed, the context class, what the heck is the context class? That's undefined here, but I guess that is this class here. It says context, this class here. Calls the appropriate methods of the strategy object. That one is a little hard to understand for the layout manager. I mean, for sure, the container is going to say, layout container of this. What the other ones are good for is not totally clear, right? Because we don't really know the context of layout all that well. So let's go to this other example where it is a little bit clearer, namely the sorting. So in the case with the sorting, who benefits from pluggability of the comparison? Is it the country class? Is it the collections class? Or is it the comparator class?
The collections?
I would say it's the collections class because the collections class has a job to do. It has to do the arrangement and sorted order. But I mean, I could take your point to say, well, the country class, of course, is keenly interested in being correctly sorted. And so if one takes that point of view, then the pattern would work a little bit differently. Remember when we talked about interfaces at first? We said that there is the comparable interface, and countries are comparable. So if a country wants to say, I want to be sorted in just the right way, and the one and only true way, then the country would implement comparable. The difficulty with that is when we then get to part 2. If one also wants to make the comparison pluggable, well, then it can know the country part, or the country class, they can only be comparable in one way. And it's that difference here that says that the comparator is an example of the strategy pattern, whereas comparable is not an example of the strategy pattern, because you can't change the strategy. If you have a bunch of countries, and if you just use the intrinsic ordering, there's only one way of doing it. So in this case, then it is, I guess, the collections class that benefits from the pluggability. And so over here it says whenever the algorithm needs to be executed, that's the sorting algorithm, the context class, that's collections, that's good, calls the appropriate methods of the strategy object, which would be, what's the method? Compare. Yeah. So when you read through this, like I say, read through it with a pencil in hand and try to make this match up with your own brain. In fact, it's probably a really good idea not to look at this table. Try to see if you can reconstruct it yourself. Cover it up and try to do that on your own. That way you learn. Okay? So when with these textbooks, they do put in all of the stuff, but sometimes it really is a good idea to say, can I just work this out by myself? And probably you won't. You'll make some misstep somewhere. And then the difference between what you have worked out and what's actually in the book, that really gives you a good handle on where you need to study further. If you don't work it out yourself, then it all makes too much sense. And that must have happened to you. You read something and say, this all makes so much sense, and then when you actually have to apply it, then it doesn't really work out. That's whenever I read through the Amazon documentation, when it's at a high level, and then I do try to formulate some guesses. When it's at a more concrete level, then of course things are much happier. Then I can just sit there on the terminal and try stuff out. And I do that. I read a little, I try something out, it doesn't work, and then I get the instant feedback that way, that I was on the wrong track. And it's really important that you try to get yourself some way of getting some feedback. And in a textbook, there's no dialog boxes or anything that you can type something in. You have to get yourself into situations where you get feedback of whether you're on the right track. And that sometimes actually means on a piece of paper or something, try to recreate some of those things. It is important. And it's tedious, right? So you can't expect to be done in 15 minutes. It really is tedious and time-consuming. All right, on to, I have two, in the homework. Where's the homework? Because there is a different strategy. What's the strategy in the homework that we want to modify? So in the homework, what we have is, this is from a modification of a lab where there were a bunch of animated things. There's one thing here and whatever, some vehicle there, and so they kind of move around. And so what do I do every second? I called move, and then again I call move, and I call move, and they move. So the basic strategy is just call move on all elements. Now, what other strategy might one want to have? I gave us another example of a strategy that when they're at the boundary, then they should stop moving. So there the strategy for updating is, if it's at the boundary, don't move it, otherwise move. Or I could have a strategy that says, if they collide, if the bounding rectangles overlap, then have both of them stop. I was thinking of, it would be nice to have a strategy where it says, then both of them move in the opposite direction, but there's nothing in the interface that lets me do that. I would have to enrich the interface of movable, whatever it was, movable shape, to say revert or, and I didn't want to do that. That would be more realistic, right? Then they could like bounce off each other or some such thing, and that would be a nice enhancement for an exam. But in this homework, the strategies have to be expressible with what the movable interface is. Yeah.
A little bit off question from the strategy video, but would you be able to post the that in modification code? I did the hack.
Okay, put a question on Piazza. Say how far. What was? I mean, with these things, I always like to have a give and take. You say this is how far I got, and then I give something.
Yeah,
Okay. And yeah, I mean, there's nothing that I wouldn't want to give on. But I think just in general, if you give me something, I'll give you something more. That way, it starts some kind of a discussion. And like I say, it's completely anonymous, and if I will not remember who asks me questions, and if anything, I will remember it with gratitude. So you should always feel free to ask questions on Piazza. You can make it not anonymous if you want your classmates to love you in person. It doesn't have to be anonymous. And that's actually in a senior level course. I always make a big thing out of getting people so that they start asking questions on Stack Overflow, where the questions on Piazza are not anonymous, and where we'll go through how to ask good questions. So it's good practice for that. It is super important that by the time that you graduate, that you can ask good questions on Stack Overflow, because there's no life without Stack Overflow, right? I mean, you can't survive without Stack Overflow. You really can't. Right? There's an infinite amount of technical minutia, and no one of us can know all of them. So start asking some bad questions or some iffy questions, and I will answer. So the strategy here was this: how should the update happen? Maybe another strategy might be that when they collide, they both poof go away. I don't remember if the interface that I have is rich enough for it might because there's an ArrayList that's passed. I guess you could just remove the things from there. I'll try that just for fun. So that's a pluggable strategy. In different program runs, we may just want to have continuous motion. We may want to have motion that stops. Another way of doing it is I could stop the motion after 100 moves, or I could make the first object run twice as fast as the second, or whatever crazy thing I want to do. Randomly do it or not do it. So all of those motions are different strategies that should be pluggable. All right, next pattern is, containers and components. So in Swing we have components like buttons, and we have containers that can hold buttons. And the idea of what's called the composite pattern is that a container should itself be a component. Why?
Nested container.
So you can nest them. That's exactly right. And so if you look at that wonderful user interface here, the container here is also a component that is in this bigger container. Same thing with this one. This here is a container that's also a component. So containers should also be components. And the way you do that is pretty simple. That you have, do I have the UML for? No, I don't. Okay. So if this here is the component interface, then the container extends component. And also a container has components. In the language of the pattern, one talks about the thing that both is and has the smaller things, the composite, and the general thing you call the primitive. And so we generally like this to be an interface. It happens not to be an interface in Java with containers, but in general that's the preferred implementation. And so then the ones that are concrete components but not containers, we would call those leaves. This is one of the leaf classes. There'll be many leaf classes, one for each. So that's a generally very, very common pattern that anytime that you want to nest things that you use, where the thing that has lots of things inside, as you can see here, that you also want it to be one of those things. See, is there any other example that we know? Like is an array list? Is that an example? Like a Java util array list? So let's say an array list of strings. It has strings, but is it a string? No, so that doesn't really work, right? So there actually aren't that many examples in that you know right now, but I'll give you an example. Sometimes when you want to read one file and then another file and then another file, there is a thing in the streams in the I/O library where you can make a stream that's composed out of multiple streams, and that itself is a stream, where you just use the regular old stream API, and it reads through the first one, then through the second one, then through the third one, and so on. That can be useful. The one in the homework is very visual, and it's kind of the same thing as the components and the containers, and that is when you have a bunch of shapes, like here we have a cloud, and we have a car, and we have whatever, another cloud, and the sun. Each of those are individual shapes, and then I want to make it so that the whole thing is also a movable shape. And at this point, it's a little bit hard to see what's the use. I'll come back to that in a minute. Because how do you move it? You have to call move on each one of them, and it's not clear that they're going to move in unison. Like the clouds aren't going to move at all, and the car is going to move. But there is a reason why this is useful that we'll see in just a minute when I get to the next pattern. So the last pattern that we have is the decorator pattern. And so I'm motivated again with something that's in swing, namely scroll bars. So there, in different user interface libraries do this differently. The way this is done so you all know what scroll bars are, and you have these things here, and so let's say you have a text area, and it's getting kind of small, then you want to be able to scroll to the other text. So the way this is done in Android, for example, is just like this. The text area, you can say, I want scroll bars, and then the text area gets scroll bars. What if it's not a text area? What if it's a drawing? Well, Android does have a drawing class, and yes, you can give it scroll bars. What if it's a table? Android has a table class, but it doesn't have scroll bars. They didn't think of it, for whatever reason. What if it's some component that you designed? Well, by itself, it doesn't have scroll bars. If you want scroll bars, you have to go through the labor of figuring out how to put in scroll bars. So the Swing designers did this much better. In Swing, they said, any component can have scroll bars. And the way we do that is to make it so that if you have any component at all, then we give you a thing around it that's called a scroll pane. And so you stick your component inside, you make a scroll pane, and then you get something that has your thing inside, and the scroll bars around. So you want to have a scrolling table, you want to have a scrolling diagram, you want to have scrolling text, whatever it is, you put it inside this scroll pane. And the beauty of that is what comes out of it is, again, a component, which means you can now take this thing and stick it inside a container. You could, of course, put another set of scroll bars around it, which I don't think anyone would do. But it's a completely general mechanism, and that's its beauty. So we take a component, and we change it into a different component. And the design pattern is called the decorator pattern. And so here you can obviously see that the decorator is meaningful, right? We're decorating this component, and out comes another more decorative component, right? It's decorated with these scroll bars. And so the decorator pattern is probably one of the easiest to remember patterns. Just think scroll bars. Any component goes in, component with scroll bars comes out. The basic component is here. The J scroll pane has one component, namely the one that's being decorated, and it also is a component. Yes?
Isn't it kind of weird to call it decorated though? Because that's what implies that it's just a visual thing. The
Yeah.
scroll bars actually give you something useful.
Okay, that's a good question, but all of the patterns are like that, right? We had the strategy pattern. Is it strategic? I mean, maybe it's tactical, right? So with all these names, they had to come up with names that are kind of memorable, that are good handles for this concept, but they can't all completely describe. The same thing with composite. I mean, there's multiple ways you can think of something being composite. So the decorator, is, you can argue, is it decorative? Is it whatever? That's just the name. But given that they had to give it a name, I thought one might as well think of a situation where where it does in fact add something onto it. But I understand what you're saying. It's not just for beauty; it's also for functionality. So you can't take those names super seriously. I'll give you in context in just a minute where it is pure decoration. All right, so the decorator pattern here is spelled out. Component objects can be decorated. Here, see, it says visually or behaviorally enhanced. So, enhanced in some way. So the decorated object, we want it to be able to use it in the same way as the undecorated object. And that is the key part of the decorator pattern, that we don't want to change its nature. It should still be a component. The component class doesn't want to do anything. That's another important part of the decorator pattern. The JText area knows nothing about the scroll bar. It does not know that it's been decorated. It didn't have to be modified. And then this kind of general mumbo jumbo, there may be maybe more than one set of decorations. In the context of Swing, there actually aren't that many decorators, and the textbook later goes out with a counterexample, and I know we'll get to. Now, back to my exercise here. I'm going to make you do one very simple decorator where you take a shape, like this cloud shape here, and the decoration that you will apply is to put a box around it. By default, the box fits tightly, but you can also make it so that there's a little bit of a gap. Okay. Now that is clearly decorative, right? And it has no particular functionality. It's just there for the decoration. That's the decorator that I want you to apply. And now back to the composite pattern. I said previously that if you take a bunch of shapes and turn them into a single shape, that you don't see a lot of benefit with the moving and drawing. But actually now if I just take this thing and say decorate this shape, then it'll make the box around all of them. So that's where you will be able to visually see that the decoration works. And that's also where I will be able to, because I'll be testing that, I'll be able to make sure that your composite shape is a shape. Otherwise, it wouldn't be decorable. And I'll make another one where I take one of these things and just put two borders around it. Again, for that, the decorated thing has to be another movable shape. And of course, you'll have to make the work so that when the box shape moves, you have to move the box. You don't want the cloud to escape the box. That's something you will have to do. All right. So in the context of the homework, we have three different patterns. Pattern number one is the strategy pattern that says, how should these things all move? And realize that the strategy is very limited by the API that we have. We can't move these in arbitrary ways because the only tool that we have is to call their move method or not. And I guess the other tool that we might have is to just remove them completely from the setup. We have no in the API for moving. We have no way of absolutely moving them. That'll have to be reserved for a different assignment. So that's number one, strategy. Number two is the composite, where we take individual shapes and make them into a big shape. And number three is the box shape, where you take a shape and you apply decoration to it. So each of those is a manifestation of a design pattern. And so it'll be a really good exercise to go through these design patterns and make these little tables with the homework. I'm not forcing you to do it. I'm just saying it's a really good idea, because that way, you have a way of kicking the tires of this and reading through these things in an intelligent way. Now there is another and maybe surprising way that the decorator pattern applies, and that again is the reason why we're learning it, and that is with Java input streams. So you may know that in Java you have streams and readers. A stream reads bytes, a reader reads characters. There's a way of taking a stream and turning it into a reader. That's what we're doing here. So you have system.in, which is a stream. Kind of annoyingly, now we're turning it into a reader. And now we have a reader, and it reads characters. Now, if we want to make it into a better reader, into a more capable, more functional reader, there is this decorator called buffered reader. The buffered reader takes a reader, and it produces a reader. Why is it better? Let's actually look at buffered reader.
It has classes like read line.
It has a extra method. That's one thing.
Methods.
Yeah.
Why is buffered reader not an iterator? Why didn't they implement iterators?
Okay, that is a very good question. Look, let's first get everyone on the same page here, and we'll talk about that. So a buffered reader has a method called a read line that, weirdly enough, the basic reader doesn't have. And that is why if when like from Java 1 on, I think when these things were introduced, people used buffered readers because they wanted to be able to read a line at a time. Nowadays we normally use a scanner because a scanner has a much richer API, but the buffered reader was where it was at then. So why is it buffered?
It doesn't read the whole input all at once.
All right, so here's how the buffering goes, and that's a general concept. So what a reader does is, if you have some input, and you ask it to read, it reads a single. Let's say it reads a single character. It makes it easier to understand. They actually read bytes, but work with me here. Let's have them read characters. So then it would read the H. Next time you say, give me something, it would then read the E. And each time, potentially, to read something from a file, it would be a system call. And so each time it would have to go out of the Java virtual machine, into the operating system, grab a character, and come back. So that could be costly. And so what a buffered reader does is, when you ask it for the first time to read a character, it's going to read 1,024 characters and put them into an internal buffer that it keeps for its own private use. And then when you say, give me the first character, then it's going to give you the H. And the next one, it's not going to go and get more, but it's going to get the E. And after 1,024 times, then its buffer is going to run out. Yes, sir?
Isn't buffered reader, doesn't it contain like another reader that actually reads the individual?
Yes, so it'll defer to filling up the buffer. That'll be the original reader.
Well, you said that it's slow if it keeps reading individually, so then how does it make it not slow?
Oh, because it really is no slower to read 1,024 than it is to read one. So when you need to go down to the operating system to get a bunch of bytes, you might as well just ask for 1,024.
Okay.
You get them at about the same time as you get one, because the cost of going to the operating system in the first place is so high.
10, 24 bytes.
Yeah, I mean, you could get 1 million, right? But I mean, somewhere there is some compromise. So they read some reasonable buffer size, so that the cost of getting them is is not incurred every single time. I mean, it's just something like, when you go to Costco, you get, a 24-pack of toilet paper, and because the cost of the trip to Costco is so, is something that you need to put in mind. Yeah?
I don't understand why this can't be implemented as an iterator.
Okay, so a couple of things. So I'll talk about that in a minute. The first thing I want to point out is that even though the people who designed the stream library will tell you that this is great because it's an example of the decorator pattern, they are right that it's an example of the decorator pattern, because the thing that you put in here is a reader, and the thing that comes out is again a reader. So yes, it is the decorator pattern. But the thing that is daft is, why doesn't every reader buffer? That is such a fundamental thing. In C++, every reader, or the equivalent of reader, every input stream buffers. It would be so weird not to buffer that they just never, that never occurred to them. Why doesn't every reader give you a full line of text? That is such a common operation. For that matter, why doesn't it just give you an array of all, or a list of all the lines? I mean, who wants to read them always a line at a time? Why doesn't it give you, to your saying, an iterator through all of the lines? And that's just bad API design. That it would have been equally easy to say that a reader should give you, should do the buffering, should do the iteration. For that matter, have a convenience method that just gives you a list of all of the lines. I don't know the last time that I enjoyed having to read them one at a time. Sure, if you have a very large file, then it makes sense that you want to lazily read only as many as you need, because maybe after line 20 you decide you don't need to go any further. So having the choice between an iterator and a list would be great. But nowadays with default methods, that's an easy thing to do. Right? You have a fundamental method that does the iteration, and then you have a default method that uses the iterator to pour them all in a list. And now, of course, now in 2017, when we look at the API, someone has has realized that, and nowadays you can get a lazy stream of strings with all of the lines, and that's pretty good. It would have been even nicer if they had added this into the basic reader and not to the buffered reader, because you still have to do the buffered reader thing. And now you have the awkward choice that you have the scanner API, which gives you one set of benefits, and the buffered reader API, which gives you a different set of benefits, and you have to then fret over which of the two you want. I mean, the scanner gives you a bunch of other useful stuff. The one reason that people don't always like to use scanners is that scanners scan with regular expressions, and that can be slow. But that's an implementation detail that any competent programmer could have figured out how to overcome. So this whole API here could have benefited from, I think, a little bit more love and foresight. But be it as it is, many people are familiar with the buffered reader thing, and it's an example of a decorator. If you've never seen it before, it's not going to be your favorite example of a decorator. But if you happen to be familiar with it, it gives you another idea of what a decorator is. And I like this example because clearly this is not particularly decorative in the physical sense, right? But it does show that it adds capabilities. All right, that brings me to the end of this. So look through the exam, read through that section in chapter 2 on sequence diagrams, draw the correct sequence diagram and then compare it with mine. If you can get the exact same sequence diagram that I have, that's great. If not, ask a question on Piazza. Without peeking, right? And read through this section here one more time carefully. Well, that's a lot of stuff here. I don't know how you're going to get all of it, because that's also reading for Wednesday. All right, so we're going to collectively practice that reading part.
What is the synchronize thing used for in this?
Yeah.
I saw that in the Java source code, and I've never seen synchronize.
Now we're going to see that later. Hang on just a second. I'm a little nervous here because I don't see why it's not stopping the video. Ah.